So let's go ahead and wrap this unit up by looking at some molecules and using the structure of those molecules to predict the strength of intermolecular forces. And from that prediction, we can predict the trends in melting and boiling temperatures. Okay, so let's start fairly simple. Let's think about a compound, methane. Okay, so when you're trying to identify intermolecular forces, the very first thing you want to do is to draw out a Lewis structure. Okay, and I strongly encourage you to do so with the three-dimensional structure implied. Okay, so methane is a tetrahedron around carbon, all bonds being CH. Okay, so once we have this drawn out, the next thing we want to ask ourselves is, are there any polar bonds? And remember, the definition of a polar bond is one where the difference in electronegativity is greater than 0.4. Okay, so CH bonds have a difference in electronegativity of 0.4. So there's no polar bonds here. So every single bond is nonpolar, making methane nonpolar. And since we have a nonpolar compound, the only intermolecular force that it can experience is London dispersion forces. So I'm going to abbreviate this LDF. Okay, so methane would experience London dispersion forces only. Let's compare this to ammonia. Okay, so ammonia is NH3. We have a central nitrogen with the overall electron geometry around this nitrogen being a tetrahedron, except that fourth bond is replaced by a lone pair. So this molecular geometry is trigonal pyramidal. Okay, so the question that we need to ask ourselves is, are these bonds polar? An easy thing to remember about nitrogen, oxygen, and fluorine is that essentially everything bonded to these three elements is polar. So NH bonds are definitely polar. So we can imply that on our structure by showing these arrows, where the arrow is pointing towards the more electronegative atom. Okay? And since this compound is not perfectly symmetrical, then this compound is polar, right? So these dipoles don't cancel out, so ammonia ends up being a polar molecule. Okay, so then to assign intermolecular force, we have a polar molecule, so it experiences dipole-dipole. I'm going to abbreviate this DD. Okay, remember, every single compound experiences London dispersion forces. And here, in this case, what we notice is that we have a nitrogen attached to a hydrogen. And remember, when we have nitrogens attached to hydrogens, the compound can experience hydrogen bonding. So in addition, we have hydrogen bonding. Okay, so this compound experiences dipole-dipole, London dispersion forces, and hydrogen bonding. And the strongest of these intermolecular forces is hydrogen bonding. So when we try to predict whether ammonia will have a larger or a smaller boiling point than methane, we think about the strongest intermolecular force. So ammonia has stronger intermolecular forces than methane because hydrogen bonds are stronger than London dispersion forces. So we would predict the boiling temperature and the melting temperature of ammonia to be larger than the boiling temperature and the melting temperature of methane. Okay, so let's think about this compound. So we have CH3OCH3. Okay, this compound is known as dimethyl ether. Okay, so if we were to draw out the Lewis structure, okay, so remember the connectivity of these, you have the carbon attached to each of the three hydrogens, attached to oxygen, attached to carbon, and then this carbon is attached to each of these three hydrogens. So we have a central oxygen attached to a carbon and a carbon, right? So this is our core structure. and then each of these carbons is attached to a hydrogen. And if we wanted to show 3 dimensions, we could show it like this. Everything attached to oxygen, except itself, is a polar bond. So this is a polar bond, and this is a polar bond. So this is a polar molecule. So we experience dipole-dipole. Everything experiences London dispersion forces. And if you have dimethyl ether interacting only with itself, these are all of the intermolecular forces it will experience. So the strongest is dipole-dipole. So if we were to predict whether ammonia has a larger or a smaller boiling point, ammonia experiences hydrogen bonding, but dimethyl ether does not. So ammonia experiences stronger intermolecular forces than dimethyl ether. So we would expect ammonia to have a higher boiling point. Okay, so one last thing to think about when we're thinking about hydrogen bonds. Okay, dimethyl ether, by looking at it, you wouldn't think that it necessarily experiences hydrogen bonds. But the reality is that it can be a hydrogen bond acceptor. Okay, so when we're dealing with hydrogen bonds, they come as donating molecules, so we can have hydrogen bond donors, or we can have hydrogen bond acceptors. Because remember, hydrogen bonds are shared hydrogens. So we have a hydrogen that's covalently bonded to one atom and non-covalently bonded to another one. Okay, so the idea here is that this would be our hydrogen bond donor, and this atom right here would be a hydrogen bond acceptor. So if anywhere in your compound you see an NH, an OH, or an FH, then this bond is a hydrogen bond donor. But some compounds are able to hydrogen bond even if they don't have one of these bonds. All right, so if you have something like dimethyl ether, so here we have oxygen with lone pairs, making it able to reach out and accept a hydrogen bond. So dimethyl ether is a hydrogen bond acceptor. So if it's in the presence of a hydrogen bond donor, it can still make hydrogen bonds. Okay, so this is a really important concept to think about as we move forward and think about how intermolecular forces play a really important role in the structure of biomolecules. With hydrogen bonds, you have to think about donors and acceptors.